Shear, a second important factor to be considered when determining the strength of beams. An internal shear force V generally is present and in some cases may govern the design of beams. Many materials such as wood are primarily weak in shear. For this reason, the load that can be supported may depend on the ability of the material to resist shearing forces. Beams are normally horizontal. Cross-sections upon which bending stresses are investigated are vertical. These shearing stresses in beams are generally referred to as vertical or transverse and horizontal or longitudinal. Transverse shear action is a pure shearing condition and occurs even when there is no bending of the beam. However, beams do bend, and when they do, fibers on one side of the neutral axis is placed in compression and those on the other side are placed in tension. In effect, the fibers on either side of the neutral surface tend to slip in directions opposite to one another. Longitudinal or horizontal. The existence of horizontal or longitudinal shearing stresses in a bent beam can readily be visualized by bending a deck of cards. The sliding of one surface over another, which is plainly visible, is a shearing action that, if prevented, will set up horizontal shearing stresses on those surfaces.
Relationship between transverse and longitudinal shearing stress. This section will now show that at any point in a deflected beam, the vertical and horizontal shearing stresses are equal. Therefore, the shear V diagram is a representation of both transverse and longitudinal shear along the beam. Consider a simply supported beam as shown. V is equal to the summation of FV times area, where FV is equal to the unit shearing stress and A is equal to the cross-sectional area of the beam. Removing the small elemental square from the beam, we draw an FBD showing the forces acting on it. As shown on figure 8.17, assume that delta y is equal to delta x, and that the elemental square is very small. FV is equal to transverse shear stress. For equilibrium vertically, we arrive with this formula. To place the elemental square in rotational equilibrium, sum moments about point O. Summation of moments at point O is equal to 0. FV1 times delta x is equal to FV3 times delta y. But delta x is equal to delta y. Therefore, FV1 is equal to FV2, equal to FV3, and equal to FV4. Shears FV3 and FV4 form a counterclockwise couple. From the preceding example, we can conclude that F transverse is equal to F longitudinal at a given point along the beam length.